1894, a microbiologist named Henk Jonkers at Delft University of Technology in the Netherlands discovered something that should have changed the construction industry forever. He found a species of bacteria, Bacillus pseudofermus, that eats calcium lactate and excretes limestone. Living bacteria that produce stone. He mixed these bacteria with their food source into concrete, and when the concrete cracked, moisture seeped in, activated the dormant bacteria, and they literally healed the crack by filling it with fresh limestone. Self-healing concrete. He published the research. The construction industry yawned. Then they buried it. The reason is not complicated. The American concrete repair industry is worth $25 billion per year. Every cracked driveway, every spalling bridge deck, every deteriorating parking garage generates revenue. Concrete that heals itself generates zero follow-up revenue. The economics of self-healing concrete are devastating to every concrete contractor, every repair material manufacturer, and every infrastructure maintenance budget that justifies its own existence. A product that eliminates the need for its own repair eliminates the need for the people who sell repairs. Conventional concrete fails because of a fundamental design flaw. Portland cement, the binding agent in all standard concrete, shrinks as it cures. This shrinkage creates microcracks, invisible to the naked eye but large enough for water to penetrate. Water enters the cracks, freezes in winter, expands by 9%, and widens the crack. Salt from road treatment accelerates corrosion of the steel reinforcement inside. Each freeze-thaw cycle makes the crack larger. Within 10 to 20 years, those microcracks become visible cracks. Within 30 years, chunks of concrete begin to spall off. The design fails by design. Not because better alternatives don't exist, but because failure creates a recurring revenue stream. Here is how bacterial self-healing concrete works at the molecular level. Bacillus pseudofermus is an extremophile bacterium. It survives in highly alkaline environments, which is critical because fresh concrete has a pH of 12 to 13, nearly as caustic as bleach. Most bacteria die instantly in that environment. Bacillus species form endospores, dormant shells that can survive extreme pH, extreme temperatures, and complete desiccation for over 200 years. When the concrete is mixed, the bacteria encapsulate themselves in spore form and go dormant. They wait. When a crack forms, water and oxygen penetrate the concrete and reach the dormant spores. The moisture activates the bacteria. They begin consuming the calcium lactate that was mixed into the concrete along with them. Through their metabolic process, they convert the calcium lactate into calcium carbonate, which is limestone. Limestone is chemically identical to the calcium compounds in the original concrete. The bacteria literally manufacture new concrete filler from the inside. The crack seals. The limestone bonds with the surrounding concrete at a molecular level. The repair is permanent. The process takes 3 to 8 weeks for cracks up to 0.8 millimeters wide. But here is the remarkable part. The bacteria remain viable in the concrete for at least 200 years. Every time a new crack forms, the process repeats. The concrete heals itself again and again for centuries. The Pantheon in Rome is 1,800 years old. Its concrete contains natural limestone-producing bacteria that were accidentally incorporated from the volcanic ash used in Roman concrete. That is why Roman concrete has survived nearly 2 millennia, while modern concrete begins failing in decades. We have known the answer for 1,800 years. Now here is the $1 version. You do not need a laboratory. Bacillus subtilis, a close relative of Bacillus pseudofermus, is sold in garden stores as a soil amendment for about $1 per packet. It is marketed as a natural fungicide. The same bacteria, the same calcium carbonate-producing metabolism. Mix the powder with calcium lactate, which is available as a food-grade supplement for about $0.50 per ounce, and add both to your concrete mix. For each cubic foot of concrete, add 1 teaspoon of Bacillus subtilis powder and 2 tablespoons of calcium lactate powder to the dry mix before adding water. The practical applications are immediate. Cracked driveways, cracked foundations, cracked basement floors, cracked sidewalks. Instead of paying $500 to $2,000 for a contractor to inject epoxy into cracks, you can mix a bacterial paste for about $1 and paint it into the cracks. The bacteria activate when they contact moisture in the crack, consume the calcium lactate, and produce limestone that fills and seals the crack. The repair is stronger than epoxy because limestone bonds chemically with concrete, while epoxy only bonds mechanically. For new concrete work, the bacteria can be incorporated into the mix at the time of pouring. The additional cost is approximately $1 per cubic yard of concrete. A typical residential driveway uses 3 to 5 cubic yards. For $5, your driveway has biological self-healing capability for the next 200 years. Compare that to a conventional driveway that will crack within 5 to 10 years and cost $300 to $800 to repair each time. Over the lifetime of a home, bacterial concrete saves thousands of dollars in repair costs. The science has been validated repeatedly. In 2015, Jonkers was awarded a European patent. In 2019, researchers at the University of Bath in the UK confirmed that bacterial concrete with Bacillus species can heal cracks up to 1 millimeter wide. In 2021, a study published in the journal Construction and Building Materials showed that bacterial concrete had a 25% longer lifespan than conventional concrete in accelerated aging tests. The American Society of Civil Engineers gives U.S. infrastructure a grade of C-. There are 617,000 bridges in the United States, and 42% are at least 50 years old. Roughly 7.5%, or 46,000 bridges, are classified as structurally deficient. The repair cost for American bridges alone exceeds $125 billion. Bacterial concrete could prevent most of this deterioration from occurring in the first place. Beyond Bacillus, other biological repair mechanisms exist. Fungal hyphae, the thread-like structures of certain fungi, can grow into concrete cracks and deposit calcium carbonate as they metabolize calcium-rich solutions. Researchers at Binghamton University in New York demonstrated that the fungus Trichoderma rheaceae, when incorporated into concrete, can seal cracks through biological growth. The fungal approach has the advantage of filling larger cracks, up to 2 millimeters, because the hyphae physically span the gap before depositing mineral. The connection to Roman concrete is not coincidental. Roman concrete used volcanic ash called pozzolana, which contained both the alkaline minerals and the biological organisms necessary for self-healing. When seawater penetrated Roman marine concrete, it triggered a chemical reaction that grew aluminous tobermorite crystite crystals within the cracks, actually strengthening the concrete over time. Roman harbor structures that have been submerged in seawater for 2,000 years are stronger today than when they were built. Modern Portland cement concrete exposed to seawater begins deteriorating within years. We replaced a 2,000-year proven formula with a 200-year-old formula that fails in decades. That is not progress. That is planned obsolescence. The repair paste recipe is simple. Mix 1 teaspoon of Bacillus subtilis powder with 2 tablespoons of calcium lactate powder. Add enough water to make a thick paste. Clean the crack with a wire brush to remove loose material. Paint the paste into the crack. Cover with plastic to retain moisture. Wait 4 to 8 weeks. The crack will fill with white calcium carbonate limestone. For deeper cracks, pack the paste in layers, allowing each layer to set before adding the next. For a preventive treatment, dissolve calcium lactate in water at a ratio of 1 ounce per gallon. Add 1 teaspoon of Bacillus subtilis powder. Spray this solution onto existing concrete surfaces. The bacteria will colonize any existing microcracks and begin producing limestone before the cracks become visible. Apply annually in spring. Estimated cost per application for a typical driveway: $0, $50. The construction lobby has a $25 billion annual reason to ensure you never learn this. The cement manufacturers have no interest in concrete that does not need to be replaced. The repair contractors have no interest in cracks that heal themselves. The engineering firms have no interest in infrastructure that does not require expensive rehabilitation contracts. The bacteria cost $1. The chemistry is proven. The history is 1,800 years old. The only thing standing between you and self-healing concrete is the industries that profit from concrete that breaks. What cracked surface in your home could you heal for $1?